Hello, thank you for watching our presentation. I'm Mikey.
And I'm Vimanyu.
The authoring tool that we have developed under the guidance of Dr. Lane is called Locosoft. Let's first look at some of the results. In the first two videos, you can see our tool being used to simulate arbitrary geometry such as letters. We have provided basic collision and contact handling with the ground plane with adjustable contact forces. The two simulations differ in their Young's modulus value, with the one on the right being much stiffer than the one on the left. In the remaining three videos, we are showing the capabilities of our authoring tool to fix vertices through constraints and apply user-assigned time-dependent forces. Through these features, we can author interesting motions like stretching, hopping, and jumping. Through our project, we aim to provide animators and artists a flexible tool to easily generate interesting motion on soft bodies through deformation. The main features of Locosoft include real-time tetrahedralization of arbitrary meshes, FEM simulation on 3D solids with various control parameters such as Young's modulus for stiffness, Poisson ratio for volume constraints, friction restitution for contacts, and many others. We have also provided choices of time integration techniques and a choice between co-rotational linear FEM and mass spring systems for simulation. Our tool also allows the user to fix vertex positions through constraints and add time-dependent user-defined forces to author simple yet interesting locomotion behaviors. Lastly, we have incorporated the functionality of baking the results from the simulation through Alembic. The paper that we have chosen for this project is called Deformable Objects Alive by Koros et al. From SIGGRAPH 2012. The main ideas of the paper involve soft body simulation for 2D curves, 2D shells, and 3D solids. The paper also provided details on the control of soft body deformations by adapting rest shapes and support for various controllers. For Locosoft, we implemented a subset of ideas from the paper, namely FEM simulation for 3D deformable solids, and we provided a workaround technique for generating various motions such as jumping, hopping, stretching, and like the ones mentioned in the paper. Now let's see how our tool can be used in Maya.
We have prepared a sample scene with a polygonal cube and a ground plane. Now we are going to show you how to deform this cube using our system Locosoft. First, we are going to tetrahedralize the cube using Locosoft's tetrahedralize feature. Once we have this tetrahedralized geometry, we are going to show you live tetrahedralization. So for that, we are going to deform the original mesh. We are going to choose vertices, and we are going to increase the base a bit wider, and we are going to increase the height. You can see the tetrahedralized geometry change on the fly. Once we have a tetrahedralized geometry, we are going to use Locosoft's simulate tet mesh option, and let's play the simulation. Let us make this object hop now. For that, we are going to use user control forces on this object. First, we will select the vertices and select Locosoft force vertices option. These are the vertices on which your forces will act. Then we will enable the forces in our solver, and then we are going to set certain force parameters which will help you control the user applied forces. For additional information on these attributes, you can refer to our documentation. Once we have the parameters ready, and once we have the control forces ready, let us try to simulate this. Alright, let's see the simulation. As you can see, the top three vertices on the left are applying a downward force periodically, and as a result, the object is hopping to the left. Next, let us reduce the Young's modulus to 30,000 from 50,000, and let us try to simulate. Now, we have reduced the Young's modulus, so that means the stiffness of the object is much lesser, and you can see remarkably different results from the previous simulation. As demonstrated, we have controls for materials, and we have controls for user forces in our system. Great, that was hopping. Now let's make this object jump. For that, we are going to again select vertices, and this time we are going to select the entire top row of vertices, and we are going to apply a downward force on them. The same procedure, we are going to select the force vertices, and we are going to tweak the force parameters a little bit more. And let's simulate and see. As shown, using this technique, we can create believable jumping motions for soft body characters. Next, let us fix vertices using constraints. For that, first we are going to disable the existing user forces from our solver, and then we are going to select the vertices, and using Locosoft constraint vertices and enabling constraints in the solver, we are going to constrain the vertices. Let's reduce the Young's modulus to get a little bit of wobble at the base of the object. Let us now add downward forces to the bottommost vertices. This way, we can simulate the effect of pulling a constrained object and releasing it. Let us tweak the force parameters. Let us reduce the magnitude of the force, and let us increase the release time to something like 300, and let's simulate. Here's the resulting simulation of a constrained soft body being pulled and released. Thank you for watching this presentation.